I'm really happy to be like among very extremely smart mathematicians, because formally I recently defended my PhD thesis in economics, but I'm very interested in econometrics and statistics. So this paper is basically at the intersection of econometrics and applied statistics. So the paper is basically consisting of two parts. I'll talk about dimensionality reduction first in the first part, and then I'll talk about how we could actually estimate heterogeneous or personalized parameters, given that we have the dimensionality reduction in the first stage. So the paper is still work in progress with jointly with Nicholas Possum and Vadim Sokolov. And if you have any suggestions or questions, just feel free to stop me on the way. So just to motivate, before we start to the actual model and details, just to motivate the paper, we know that when working with high dimensional data, we have common problems like the cars of dimensionality, computational complexity, invertibility problems, and so on. So the standard solution is to use dimensionality reduction methods. For example, PLS, PCA, and TSNE algorithm has been very popular recently, LDA, and some other methods. But the common limitation of these methods is that in many cases they lack interpretability of the reduced dimensions. So in some settings we would want to interpret the findings, not just the black box reduced dimensions, but we would want to have some more intuition and meaning behind those reduced dimensions. And that part would be extremely relevant for estimating parameter heterogeneity or variations of the parameters, in this case, policy effects or treatment effects, as you could imagine, across the whole space of data or the population. So we do have methods for estimating directly parameter heterogeneity or parameter variation, and Ethe and Wager have been extremely active in this field. So they come up with some generalization of the common random forest to be tailored to the parameters of interest. For example, average treatment effect or average policy effect or different parameters of interests instead of the directly outcome, just like in classical random forests. But the common limitation of this approach is that these methods are random forest methods tailored to the parameters. They choose a single dimension or a characteristic or variable at a time. So what they are doing, they are estimating the loss, picking just one covariate, and then again sequentially continuing to pick another covariate, estimate parameter, and so on until some criterion is met. So in this paper, we are three. We try to tackle both problems at the same time. First, by introducing and generating interpretable components or a combination of the original characteristics based on partial least squares, and estimate then in the second step estimate heterogeneous parameters or policy effects in randomized control trials. So the primary research questions of this paper are whether the formed components or these combinations of the factors are more informative compared to the original characteristics or features as given. The second question is whether the formed dimensions reflect the relevant features for estimating personalized policy effects. And this is a relevant question because typically dimension reduction methods are tailored to the outcomes, not the parameters. So we would want to capture information that is relevant for the outcome as well as parameter heterogeneity. And the third question is, of course, whether we could gain some economic insights into personalized policy effects when conditioned on the components or groups of formed features rather than the features originally. So the main contribution of this paper is to introduce interpretable groups of features based on partial least squares and then estimate heterogeneous policy effects within and across the formed subgroups. So I'll talk about identification of target components, personalized policy analysis, and application if time allows, of course. So the identification of target components or the combinations of features is based on the standard partial least squares method. And just to remind, so basically we seek to identify the linear combinations of the features also known as or labeled as target component scores or factors in this paper, denoted by C, and Q denotes a dimension of these components. So essentially, you could imagine that we are trying to explain the highest variation in the covariates X and also the outcome Y. So in this case, X depends on the components and multiplied by some weights or loadings, and then Y also depends on the same components multiplied by the weights. So this is just a like general structural equation model of the PLS method. Unfortunately, our model is not free of assumptions. So the very first assumption we use is that the policy is independent of the potential outcomes. So in this case, we have an unconfoundedness assumption. Basically, here yi1 denotes a potential outcome if everyone receives a policy, and then yi0 is vice versa, the outcome if no one receives a policy. So these are hypothetical potential outcomes, and this condition basically states that we have an exchangeability condition, so that we could replace potential outcomes with the observed outcomes, just like in standard RCT designs. So this is conditional on the original covariates Xi. So the second assumption is regarding the data generating process assumption. And also here, unfortunately, we don't have a fully non-parametric setting. So we assume that the outcome is dependent on the original covariates linearly, but wrapped by the nonlinear G function. So the G function maps this linear combination of X and B into the outcome, and plus we have some epsilon error. Also, the second crucial assumption here is that we assume that X is jointly elliptically distributed, and we have the pair of eigenvectors and eigenvalues where the covariance of X and Y population covariance could be written in an additive form. So, and lastly, other assumptions are adopted by Wager in the 2018 paper, which I did not really want to copy here, but in case of interest, we could discuss these assumptions further. Before I go to the primary contribution, I want to show you the algorithm that we use to detect these combinations of the features or target components to be later used in the estimation of policy effects. Here, the algorithm is not very hard. So in the first step, what we are doing is to compute basically initialize weights based on the covariance of each feature with the outcome variable. So here you see W11 tilde denotes a covariance, normalized covariance of X1 and Y, and so on until the dimension of the covariate P. And then the first target component is formed as a linear combination of the weights and the corresponding features denoted by XW1 tilde. So in the next step, we regress X on the first component, and then we regress Y on the first component to identify the weights or loadings. And then because we have this initialization scheme, of course, we have not extracted all the information from the first component. So what we do is to compute residuals denoted by X1 and Y1, and then repeat the process. So what this procedure essentially does is to initialize weights, then we compute the components as a linear combination of these weights and the covariates, and then we extract further information from the residuals that were not taken into account. So basically, this procedure would coincide with ordinary least squares if the dimensions in two approaches are the same. So just to visually show you, the aim is to, of course, capture variation relevant for both covariates and the outcome. And this dimension in partial least squares, just like in principal components, could go in different dimensions. So different extracted factors reflect different positions in the coordinate system. So this would help us actually also capture variation or information relevant not only for the outcome, but for the parameter heterogeneity that we are concerned in this paper. So the primary contribution of this paper is to show that the extracted factors or the weights are consistent, and this result is basically extension of the Helland 1990 that shows that partial least squares have an analytic solution. So you probably recognize this. It looks like an OLS, ordinary least squares coefficient. Only instead of the original X feature, parameters. We have R hat, which is a Krylov sequence depending on the variance, sample variance of X and the sample covariance of X and Y. So our contribution is to show basically that the B hat is consistent, even in this case, partial least squares case. So as promised, the second step will consist of estimating a policy effect conditional on the formed target components denoted by CI. So here you see that tau CI denotes a policy effect or treatment effect, you could call it, which is a difference between the treated and untreated potential groups. And then this could be replaced, the potential outcomes could be replaced by actual outcomes because we assume the exchangeability condition. So the whole paper is focusing on estimating this quantity of interest conditional on the groups of interest. So this is a basically group average treatment effect based on the data-driven target components. So I'll show you simulation experiments. So we have two experiments in this case, and the first one is randomized control trials. We have 4 different covariates, from X1 to X4. We have a policy PI, and then we have the outcome that depends on the first 2 covariates and the policy. So one particular characteristic in this design is that we put a lot of weights on the original characteristics, but very low weight on the policy effect of interest. And then in this case, we are interested in the power of the PLS to be able to capture the information that is X3 and X4, also relevant for the policy effect, P effect on YI, not only just X1 and X2, because in many cases, for example, if you run lasso or ridge regression, you might see that the X3 and X4 are disregarded and they just keep X1 and X2 as covariates, relevant covariates. So ideally, we want to detect information also useful for the policy effect, tau xi in this case. The second simulation design is a simple instrumental variable approach design that is just basically structural equation model where policy is driven by some combination of the 2 instruments, and we also have the latent unobserved variable UI. So in this case, simulated by normal distribution, but when we estimate the algorithm, it only knows P, Y, and all the 4 covariates that we have. So here the challenge is, of course, to see that whether the method recovers at least closer to the true policy effect, and whether it differs from the standard classical approaches that we would have. So here you see the simulation design in the case of randomized control trials, and I have different number of samples from 110,000 observations, and then you see 3 different methods here. Forest PLS is labeled as our approach that we use, that is first dimension reduction and then estimating the distribution of the parameter, that is policy effect heterogeneity as we call it. And then you see the red one represents the classical method without the dimensionality reduction called causal forest, and the orange one is a true distribution of the policy effect, the simulated one. So the advantage of our approach is that you can see that even in small sample sizes, the distribution is very close to the true one, while the original proposed by Athay and Bagger 2018 paper, the model basically captures a lot of redundant information, like, for example, the covariates that do not matter or the residuals, and it's not able to distinguish between the relevant variables and the ones that are redundant in small sample sizes. But then when the sample size gets to 10,000, all the methods become very similar to each other. Here I have 500 experiments, and these distributions are averaged across 500 different simulation designs, basically. So here you see the second one, the structural equation model, or the IV approach that we call it. essentially you see that both methods are quite bad. They don't reflect a true distribution, partly because of this unobserved latent variable that confounds the analysis if we just estimate policy effect on outcome based on the observable features. And then the point of this, of course, to show that our method is not worse than the classical method in the structural equation designs with some latent variables. So I also have we also have an application here that is basically we use the existing data, that is Pennsylvania reemployment bonus experiment that took place between 1988 and 89. And this paper describes more details than we do here. And basically the overarching aim of this paper is to test whether the cash bonus of $997 for the participants in the treatment group would aid in finding the employment. So we are testing the effect of this cash bonus on the logarithm of unemployment duration in weeks. So we have lots of different features such as age, gender, the quarter of experiment, and they enrolled in unemployment rates and other things that are also in detail described in the paper. And before we get to the distributions, I want to show you how we could actually interpret this target component. So we talked about interpreting them, and essentially what we could do is to regress each component. In this case, we have two optimal components regressed on all the available covariates. Here is not the full list, but if you look at the female, for example, just as an example, it has positive sign. So that means that when the values of the component, because this is a components are continuously distributed across some values, so it's a continuous variable, and it indicates that the upper parts or the higher values of the components are represented by female or anything else that is positive, that has a positive sign. And then if you look at black, for example, the lower values of the component corresponds to the black, Hispanic, or other race individuals that exist in the study. So the sign and the quantity of this regression coefficient tells us how much these components are driven by different groups. So essentially, these components reflect all these different groups within the original characteristics that could matter for policy effect heterogeneity. So just to sum, all in all, we have low score values that are equivalent to young male non-white participants who joined the experiment early and who have few or no dependents, and the high score values of these components or target groups are equivalent to middle age and older individuals, female white participants who joined the experiment late and also have many dependents. So here I have the primary result of this paper. It's not so pronounced in this plot, but you see that the low, so here you see on the x-axis, first of all, the vigintiles of the component, and then on the y-axis, we have policy effect. And you see that the low score values of the component, or first 5 vigintiles, have higher variation compared to the last 5 vigintiles of the component 1. And that indicates that this group, essentially young male non-white participants with few or no dependents, exhibit much more higher variation than compared to the individuals or participants of the experiment that have many dependents. And then I have the same plot against the component 2, vigintiles of the component 2, and here the variation is more pronounced. So basically the cash bonus could either increase the probability of getting the job for some individuals, and it could also decrease the probability of getting a job for other types of individuals. So there is quite a bit of variation, significant variation going on in the first group of interest. So just to summarize my findings, so the difference between the 97.5th and 2.5th percentiles of policy effects is 92.8% in the first vigintile of component 2 and decreases to 22.1% in the 12th vigintile of the same component. So essentially, the conclusion from these findings could be that there is a need for targeted or personalized measures for younger non-white male claimants. So here we also have some theoretical simulations, which I have not shown you here. And we do have some non-RCT frameworks, but the future work could be to extend the results to incorporate more cases where we don't have experimental designs, but some endogeneity, also deal with endogeneity, basically. Yeah, I think I'm actually done before the deadline. So thank you so much for listening.
Thank you very much, Maria. You are okay. Yes, you are 1 minute earlier. Thank you very much. You give us time for questions and discussion. Very, very interesting talk. Very interesting topic. Congratulations from me. Are there any questions, comments, suggestions? Okay. Zikika, if I pronounce it correctly again.
Oh, it's okay. I'm Zikica, but never mind.
Okay.
Thank you for giving me the word. I have a couple of questions, but the most prominent are basically, have you managed to establish the distribution of B hat under some assumptions? That's the first question. The second question is, when you regress C1 on something, it's probably a bit earlier, as I remember. Can you probably test if something is actually zero or not? So you have this regression, C1 equals to something previously, probably, I think. And the final question is, we can see those stars in here. So there is some sort of a test. Which test do you use if you use those p-values for something? And actually, if you do you check any assumptions under the null hypothesis, if there are any? Thank you very much.
Thanks a lot. These are very good questions, and I was almost sure that somebody would ask about the B hat consistency. We do have quite a few assumptions. So unfortunately, like as mentioned, we have not, sorry, I was scrolling down instead of up. So we have not really managed to get rid of some of the strong assumptions. So in the first case, like the first one is very standard, like exchangeability condition, just to have an RCT design and no known confounders or endogeneity problems. And the second assumption, that's where the primary core proof is coming from. So we assume that this basically the outcome is a linear function, but just the g is outside of this linear. Inside we have a linear function, but g can be anything when applied on this linear combination. So this is of course a strong assumption where we would ideally want to relax it and have just g x as just in standard random forest case. So this is partly like the proofs and results are driven by this assumption, and also like x is jointly elliptical, like jointly normally distributed, and that's also quite strong assumption. But there have been, like, not theoretically but empirically, some papers have shown that this in practice we could have some other distributions as well, and the results are not distorted much asymptotically. But of course this should be tested case by case, so we cannot really guarantee that relaxing jointly elliptical distribution would help. So here then basically like the consistency of the parameter would be coming out from Stein's lemma and some standard assumptions. So basically consistent up to a proportionality constant, where the proportionality constant converges to zero in the limit. So we do have this the DGP assumptions that guarantee the consistency, and of course, relaxing these ones, we have not really figured out how we could relax the linear functional form inside G, and which would of course be ideal for us. And then when we estimate policy effect heterogeneity, that's already a separate task here. And then we do have standard assumptions imposed by Wagner and SA 2018. Some regularity conditions and other assumptions that also guarantee the consistency of the policy effect itself. But yeah, this is a very good point. And if you have some ideas how we could actually relax, especially these two assumptions, I'm very happy to hear them. So your second question was regarding regressing the components on the covariates, right? Whether this is the ideal approach, and this is not ideal because PLS is not equivalent to the OLS, right? So in my case, I'm approximating it with the OLS regression to give some interpretation. But since we have a linear combination, so what we imagine that since we already identify some of the variables as a linear combination, then all of these variables would be important for explaining the components. So it's basically the functional form is linear. That's why we could do OLS regression there. So if we had some non-linear combinations here, then we would not really be able to run the OLS and interpret the results. But in this case, it is linear, so it's not a great loss of information that we face there. Could you remind me the third question? I don't really remember your third question.
Thank you very much for answering in detail my first two questions. The final question was actually, you have some stars in the table and you use some sort of p-values probably to test if something is zero. What test do you do? First of all, do you use it at all, or is this just the generic output? And if you do, are there some assumptions you need to check in order to use that specific test? So that was the final question. I'm sorry if it's not clear. I'd be happy to clarify.
I think I understood your question. So this is again a great point, and we are still thinking about designing this test. So it's not in the final phase, but what we have in mind is to identify. So first of all, we could basically what we could measure here is to determine a group of most important variables within a component. So if we have, let's say, we regress component 1 on 10 different variables, we would ideally want to pick up, let's say, 5 or 4 different most important variables that make a group. So the point of this test is to make some particular group, and then your question would be based on what we should make this group. So first of all, so the p-values would always be significant, right? The adjusted R-square is 1 because these components are made of all these variables, so they are always important for explaining component 1. So p-values is not the best approach, but we sought to have some threshold where we could determine that, okay, if we have, for example, some 0.1, let's say in this case 16% effect of this variable on the component 1, that would not be as important as having 36.2% effect on component 2. So we thought to have some threshold that determines which variables should enter into the group. And that's one approach. And of course, we could consider some other hypothesis testing approaches, but we have not really done so. But I think we are going to think about this, and that's a very good comment from your side. So thank you very much for your feedback.
Okay, thank you very much for this interesting discussion regarding these important issues. I think we have some time since then follows the lunchtime break. So Kimon, and then Andre.
Yes, hello. Hi, thank you for this very interesting presentation. Also, my area of research is on dimensionality reduction, so I have a lot of questions, but I will limit it to only two.
Prioritize, please.
So yeah, only two.
We have to eat lunch.
The first one is generally the assumptions that are behind PCA, PLS, LDA are a little sensitive to high-dimensional data. That you mentioned that you propose methodology to dealing with high-dimensional data. So when you have mixed data, discrete and continuous, with low sample size and also low correlations, have you checked in simulation? I saw everything works perfectly, but what's happening in your algorithm when you're using on real data, that on real high-dimensional data, how your algorithm can work with them? Have you checked their assumptions behind? I don't know if that makes sense.
That makes very good sense. Okay.
Especially linearity, that you have this ledger, for example, you're talking about linearity, but in high dimensional data that you might have of hundreds or thousands of variables, these assumptions is nowhere to be found. Also, the existence of high correlations, especially if you're in social sciences, Christina can verify, a correlation 0.3 is considered significant, while from statistical perspective, not so much.
Yes. So just to briefly answer your first point, so we do have theoretical simulations, that is to see where the distribution converges after we have 1,000. Basically, after a lot of samples, we investigate the distribution of the policy effect and whether it converges to the two distribution when we have different. So I wish I had the results here, but we do have some verification when we change the covariate distributions from normal to binary and to discrete and different combinations. So we do design those simulations, and as some other papers find, like Brillinger 2012, they also show that the linearity and the jointly elliptical assumption is not very crucial in practice, and we also verify in this paper by theoretically designing different scenarios. But what we do not test is that we could increase, for example, the number of covariates itself, right? So we fix the number of covariates and then vary the observation size. We also change the distribution of these covariates and have mixtures and non-mixtures and prove that the results are quite robust to these changes. But we do not change the number of covariates. Let's say we had 5 or 6 covariates in this case, and then we do not change to, let's say, what happens to when we have 1,000 covariates in even more. So it might be that our generated groups become quite unstable, right? And each time we run these methods, we end up with different groups. So that we should incorporate also in the analysis. The second point was about, if I remember correctly, it was about like how it performs in real data scenarios, and we only estimate these effects just for our economic, like we focus on economic interpretation rather than robustifying the method in real data, and that's also a good idea to have, for example, calibrated data, let's say parameters from some previous knowledge, and we could calibrate based on the real features that we would receive. So that's an option in our case. But for now, unfortunately, we have just economic interpretation based on the real data.
Okay, a lot of future directions.
Have you checked like to create simulations but with data from several distributions inside? Because that was my point, that in real life, in a high dimensional data set, you will end up with many distributions depending on the variables that we use. Because usually in simulations, since we create data from a specific distribution, most of the time standardized normal distribution, so it can be more easier to get a result. Why have you ever considered to create a simulation with multiple distributions inside and to see if the outcome is similar as to using only one distribution?
Yes. So the short answer is yes. And then here you see like tau xi, for example, in my case, policy effect depends on 2 different variables, like combinations of 2 variables, and then we have considered changing the distribution of each variable that would impact only the policy effect, where the rest of the variables are fixed. Let's say x1 and x2 would be fixed, but then we would change distribution of x3 and x4 and see how that differs, how our policy effect distribution is different from compared to when we have just normal distribution, let's say. So we do have these designs only in the RCT randomized control trial. So we do change distributions, but as mentioned, we do not really change the number of covariates. So we could have 1,000 here instead of 4 covariates. So 4 is very small, right? To be able to draw some very nice realistic conclusions. So that one is for future, but for the distributions, we do have designs where we test the effect of distributional changes for the policy effect at least.
Yeah. Thank you. And I will close with a suggestion to give the floor to Andre. He's raised his hand. And maybe instead of partial least square. There is also the technique that is called sparse PLS. I can send you the link in the chat if you like. So basically, I have it ready. Let me just put the send. And so basically, they create an expansion of PLS that is more robust and do at the same time dimensionality reduction with the purpose of PLS. But at the same time, if I remember correctly, they're using lasso in order to do also variable selection. So when you have high dimensional data set, it performs both feature extraction and feature selection at the same time and make all these assumptions to be fulfilled more easily. It was just a suggestion.
Thank you so much. I have to look at the paper. And so for now, we have comparison with standard lasso where
yeah, I remember that you mentioned the regularizations. Yeah.
So. But this is a very good suggestion. Thank you so much. I should look at the paper. Great.
Thank you very much for the presentation. It was very interesting, at least for me.
Thank you.
So thank you.
Well, Andre.
Thank you. Yes, I agree with Kimon. It's great to address causality topics, which is a very hot topic, I would say, important topic in present day statistics. So my questions are two. Firstly, I didn't understood quite well the actual model that you have. Is it a potential outcome? Is it a graphical model? I think it's a graphical, right? In terms of structural equations and PLS. In terms of the distinction. So it is based on graphical structural equation modeling approaches, right?
I stopped my presentation very early. I'm sorry for that. But so okay. The RCT one is less graphical. Like if you want to think in terms of the graphs, you could think of this structural equation as a graph where the some variable, exogenous variable Z, affects policy, and then policy a route to the outcome Y. So you could think of this as a graph in a 3-variable case. And also, of course, Z is independent of the outcome error terms. That's important. So indeed, that's a graph model for the IV case, instrumental variable that I designed, but the randomized control trial is we do have graphs for the potential outcomes, of course. So you could think of it as a graph as well. It's just probably just a binary case, right? The potential if everyone is treated, and then potentially if no one is treated, and then if you assume this conditional independence of those potential outcomes on P, then you can really take the average difference between the actual outcomes. So you could think of this as a graph, but that's a very simple graph then in the RCT case.
Maybe it's interesting. Those are really ideas. We have the discussion and so on. Also in the graphical modeling, maybe approaches, I don't know if you know partially ancestral graphs, it's a DAG, so a graphical model which includes latent constructs, maybe. Indeed, those are extensions also for the SEM, which uses latent variables. It's a very complex, I would say, also structure that you use. And secondly, maybe also a question, clearly you have, if I understood you correctly, some policy heterogeneity also in the component graphs. Is approach of Wager and AD sufficient here, or could any other approach to address the heterogeneity of the effects be used here? You have patient, but you have other approaches.
Yes, thank you so much for the DAG suggestion. So in the economics literature, they somehow chose to stick to the potential outcomes framework rather than the DAG version. So it's like a whole debate whether we should have one or the other. But I think it helps to have also an interpretation of the DAGs, because then we would target the paper to a wider audience, I believe. And then for the second paper, when you ask about Wager and Etheo, there are some opportunities. I don't know if you are familiar with Chernozhukov's work. So he has quite several approaches where he is testing policy effect heterogeneity. And one direction is to test our method against their method, or even replace, I think there is this generic machine learning approach that they introduce, and we could instead use this generic machine learning approach instead of the Wager and Ethé. So I would say Wager and Ethé is quite niche. The generic machine learning approach that the Chernoshogov is introducing is more broad and general, which could incorporate random forest or even deep learners or anything that you would want. So there is definitely an area to replace this Wager and Ethé with something else.
If I may just interrupt, Chernoshukov addresses high-dimensional approaches, right? So also Kimon's question could maybe be addressed.
Yeah, okay, yeah. And these directions would help also with observational data that we have discussed. Very interesting, all these issues that everyone raised. I don't have a question, and I will leave. We will leave for the lunchtime break. Just a thought to strengthen your results and your paper in its current form, because you have a lot of ideas for future direction. You could also compare with a Bayesian approach. I think you could accommodate with Bayesian priors. For example, you could examine a Bayesian regression tree that it is also used in the subject area you study. It would be interesting also to compare, I think, to strengthen the current results in this current form. You have a lot of ideas for future research studies. I think it would be of merit to also investigate or to examine the Bayesian approach as an alternative to handle this heterogeneity that you have in the hand policy effects. That's my comment on.
Thank you so much.
Great. I'm very glad.
There is also sparse PLS.
Yes,
Bayesian approach that Christina mentioned. There's also and there is a paper, I think, that they even compare these two techniques, like the simple Bayesian PLS with the sparse Bayesian PLS. So if you search this term, I think you will find the paper.
A lot of simulations to run, Maria.
Exactly. And then these are really good, right? Because like we have a direction Bayesian instrumental variable approach, for example, where I could try to incorporate the dimensionality reduction in those structural equations itself as well. So there is a big space for the Bayesian econometrics there. So thank you so much for the suggestions.
Maria, may I just additionally ask, what kind of instrumental variables did you use? Because in SEM, this is also sometimes, I think, not very clear issue. What kind of IV approach? And what kind of instruments, what kind of...
Yes, so for now, I just showed you simulations based on the instruments coming from the normal distribution, and then we have some unobserved variable that influences both policy and outcome. But you could have instruments that have any distribution, so that you could have any instrument, like binary instrument is very common in economics, and then you could have continuous instruments. So there is no restriction on the instrument. The only restriction is that the instrument should not have a direct effect on the outcome, and it should not correlate with the outcome error. That's exactly the prior conditions for the valid instrument. So in this case, we only have valid instrument, but there is this Hansen and the second Peter Rossi and Hansen paper. They relax these assumptions also for the instrumental variables. Like you could have instrument that has a direct effect based on the Bayesian prior. So you could basically have some Bayesian prior on how much the effect of instrument on the outcome should be, and then you estimate. Then of course, if you have high dimensions, we would need some dimensionality reduction method. So there is a lot of space for everything.